I didn't come here to tell you how this is going to end. I came here to tell you how it's going to begin. I'm going to hang up this phone, and then I'm going to show these people what you don't want them to see. I'm going to show them a world without you. A world without rules and controls, without borders or boundaries. A world where anything is possible.
Hey guys, James here from HACK-ATHON and welcome back to the part 2 of the debugging series. And today I'm going to go and cover a few tools that you can go and use to debug an exe application. Now if you remember, if I created a couple of applications, a couple of reverse shells rather, for Windows. One is a staged payload, the other one is a stageless payload. These two I would be going ahead and showing you a few methods to go ahead and debug those particular programs. Now bear in mind that as I'm running this on Linux and these are like exe files, I will not be able to go ahead and show you what happens in the runtime, because later in the video I would be going ahead and using immunity, which does not allow me to go ahead and run an exe program, uh, especially a reverse shell. Now, a few of my viewers have asked me how a program works, or rather, how a reverse shell works. Now, to answer that, we'll have to go ahead and first of all understand how a program memory segmentation is done in the runtime. So a program memory is actually divided into 5 sections. That's text, data, BSS, heap, and stack. Well, each statement actually represents a special portion of the memory that is set aside for a certain purpose. For example, heap is required for allocation, like random allocation of memory blocks in case memory block allocation is required during runtime. The text would store the code, like the ASM code, like the assembly code. Uh, the stack section, well, that actually has variable size, but is used in it's kind of like a scratch pad, so I should say. And it stores the function calls, and when a program calls a function, that function will have its own set of passed variables, like let's say add eax to something, to some variable, right? That would be passed along with the variables, the functions variables, in a different memory location, and that particular address will be passed to the EIP, like the EIP instruction pointer. Now the flowchart is something like this. It's always a linear process, all right? So it would first of all read, like let's say we have got 10 codes of instruction, ASM instruction. So it will go ahead and read the EIP first. The EIP would point to the address of the first instruction. So it will read the EIP, it will go to that particular memory location and load that particular instruction from that memory location, and go ahead and point up, like send that to the stack pointer, which will go ahead and execute it. Now the next step is like it'll go ahead and add a byte length to EIP, so that the EIP points to the next address location. It will address, like execute the next address location, and then it will go ahead and go back to the first step. Like this is like a linear sequence until it goes ahead and reaches the end of program, like EOP. Now there are exceptions, of course, like the linearity is broken when we come across let's say a jump instruction or a loop instruction or a go to instruction. There, in those particular scenarios, it might go ahead and jump to a random location. Let's say if we have JMP some particular address and a value, or rather EAX to a value. EAX is a register, by the way, and then a value. Then it'll go ahead and jump. It'll perform that jump location to that particular memory address with the value that is on EAX on that register, and that particular it will execute that particular program or other particular instruction, and that instruction is also stored in the memory location, right? And that memory location would be stored in the EIP, like the extended instruction pointer, and the instruction pointer would be, it will go ahead and get incremented once again, and it will go ahead and, I'm sorry, my keyboard is malfunctioning for some reason, like for the last couple of days. So yeah, the instruction pointer will go ahead and point to the next location. So this is basically how the workings of an of a program, of any executable works. Now, having said that, let's go ahead and have a look at some of the tools that we can use. I have shown you strings previously, so I'll be going ahead and using strings to debug this particular program. So if I do that, I will not get a lot of data. It's pretty much the functions that it would be calling, the DLLs, and these are the ASCII characters, which in all honesty you cannot make any sense of unless and until you go ahead and see what it is being loaded, and where it's being loaded, and where from it's being loaded. So it's like a where from and where to and what. These are the three questions. So I'll do a clear here because this is actually not of that much help, and I would go ahead and run, let's say, hexdump. Now hexdump can be run in two modes, like it has multiple modes, but I'll use the -c switch. The -c is a conversion between ASCII and hex code. So it will go ahead and show me the data in hex form, like the hexadecimal form, along with the ASCII data. So if I go ahead and do this, I would be getting the address from which this particular instruction has to be loaded, the data here, and the ASCII format here. Like the ASCII format is the normal alphabetical format. So as we can see here, it has got some text value here, it's got a lot of other things, but once again, like, this does not go ahead and give us a very comprehensive idea of what is being loaded. Like, this is pretty much in hex, and we just have the memory locations of the of where it's stored right now. Now this particular context will change when it goes ahead and it loads up in the runtime. Now as you can see, like, it will go ahead and in these kind of in these particular sections, it is going ahead and loading certain functions here, and these have certain values that or rather certain text that gets printed out by default when certain conditions are met when executing this particular payload. Now let's go a level more, one level up. Let's see what we have here. Well, we have got the sctest. Now the sctest is a very good example. Now sctest has a switch, well, it has multiple switches rather, but the switch that we are interested in is the -l switch. It will go ahead and list all the tests that it can run. If you do a sctest tac help, will get all the options. So if I do a -l, I'll get 34 options, and it will go ahead and show me which are the options that can be used. So this is a Windows 32 reverse shell, so I would be using this particular option. So what I'll be doing is I'll be going ahead and doing a -t. That's T is for the integer value, the target test that we would be running, the target test 6, and then the payload .exe. Okay, I'm sorry, I have to give VVVV. That's a verbose mode. So if I go ahead and do that, right, I think I missed out on something. Hold on. Yeah, what I missed out on was yes, this. So as you see, it's running on verbose mode 4 here, 4 V's, and this would be going ahead and giving me the CPU state. This is something that you would be seeing when I run Infinity Debugger. I'm sorry, Immunity Debugger. Uh, and it's going ahead and showing the state of the registers, the flags. The flag is like the CPU flag, what flag has been set. Once again, it's like reiterating the next state of the this particular application. The CPU state, the value of the EIP, as you can see, has incremented by 1. Like as I said previously, it will go ahead and increment by 1, and then it will go ahead and load up the values, the instructions that it has to go ahead and execute, and then increase the EIP once again. So this is one way to go ahead and see what is being loaded up and what is being loaded up where. Now let's have a look at let's say object dump. Now object dump would give us a bit more verbose output, where it'll go and show you the assembly instructions along with the addresses. For example, if I run obj-d-b binary, -b is like for the binary mode. I want to specify the binary mode, and M is like the the architecture, and the stage.exe is my application. So if I do this, it will go ahead and give me the address without the zeros, and give me the hex data and the assembly instructions. So these are the assembly instructions that we have to go ahead and execute this entire program. So if I run ASM and start executing these instructions from top to bottom, it will go ahead and give me a reverse shell. This is actually what happens in case of execution. When you do a double left click, this is what happens in the background within 1 second, and you don't even get to know it. So these are the very basic ways to go ahead and debug an application. Now let's have a look at immunity. All right. So immunity, I've got immunity installed on my Kali system. You can do that by using wine and installing that. So I'm running immunity debugger right now, and I'll show you how this thing works. Right, so this is the main console. We have got the CPU, the something that you saw previously, like the CPU main thread, where all the instructions would be loaded up. We've got file, debugger, view, plugin, imlib, options, windows, helps, etc. And these are like the shortcut. This stands for logs. This stands for E stands for, let me see, in view, yeah, executable modules. This stands for memory, and so on. So let me just go ahead and load up a program. I'll be loading up stage.exe here, and that would give me all the instructions on the main thread. So these are the instructions that would be executed during runtime. and these are the registers that you saw in when I ran sctest, and this is the hexdump. So this is kind of like an all-in-one tool that would give me a compact view of everything. Now let's have a closer look at this, right? And uh, let's see how we can use this practically to go ahead and debug and actually inject codes, your own codes in an application, and see if you get any sort of anomalies. By anomalies I mean that something that that program is not supposed to do. Let's say like if you go ahead and inject a series of instructions and execute that program and get that to run a reverse shell, that would be an exploit, right? So that can also be performed. So in case if you want to perform that, what you can do is like you can go and double left click on that, and you can go ahead and insert the instruction here. For example, let me go and instruct this instruction, and I'll fill the next 5 blocks with nops. Nops is like the no operation, which would go ahead and keep the keep the execution stale for one CPU cycle. So if I do an assemble here, I'll see that it has gone ahead and added this particular application, or rather this instruction here. And what this instruction does is like it adds the EAX to the D word, and the pointer points to this particular memory location. And DS stands for the data section. Data section is, as I've told you, the another memory section which contains the code. So basically what's happening is like it's adding the contents of EAX to the dword format of the data section. This, like whatever is present in this memory location of the data section is being added to the value in the register EAX. So if I go and add this, it will go and add this. Now if I remove this, let's say, and add this, it will go and add another program. And I cannot run this program right now, because if I run this program it will crash. It will like go and terminate, because this is Linux and this is, and I am debugging an exe file, and unfortunately immunity cannot go ahead and debug elf files, like Linux files or Unix files. So I can't show you what happens on runtime, but probably later on I'll make a video where I'll install immunity on Windows and run a program, and I'll show you what happens on the runtime. Now let me just go ahead and show you the options that we have here. So if I go view here, I get a lot of options. The first one would be the logs. The logs will go and show me what files were loaded up and from where they were loaded up. For example, stage.exe is my program name. It would be using ntdll.dll. It would be using mrcvp, or I forgot the name of that particular DLL file. Well, logs will tell me what that file is. So if I go ahead and pull this up a bit, I see that it has gone ahead and loaded up stage.exe from my debug folder, kernel32.dll from system32 folder, ntdll from system32, ws2 underscore 30, that's like the Windows socket DLL from Windows 32 folder, the msvcrt DLL from the Windows 32 program. So these are the sources. Let me just go and cancel out of this, because this does not have any practical value other than going and showing you what it does. Right. So let's look at the memory dump. This would be interesting. This would go and show me the location where they are stored right now. So as we see, like the staged, that the stage is like the stage.exe. It's stored in the text location right now. So if I double left click on this, I'll get the entire set of instructions that would be executed, which is actually this. the one that you see in this particular location in the main CPU thread. Like there would be some junk here, like these are the junks, but the main program would be starting from somewhere here. Let me just find that out. Here, the jump stage to this particular location. So the staged.exe would jump to this particular memory location, and then it would go ahead and execute whatever instruction is present on that particular location. So if I want to go ahead and let's say yeah, if I go to expression here, it would allow me to enter an expression that I want to that I want to inject rather. That can be an instruction, that can be a parameter of an instruction. If you want to go ahead, well, you cannot actually go ahead and just parameterize it. You'll have to give the entire instruction itself. So let's go back to the memory view once again. So kernel 32, as we can see, kernel 32, that this is something that's preloaded in system 32. Nothing much to talk about. This is like the hexdump that we are getting here. So this would go ahead and give you an idea of where the system files and the executable files are loaded up, in which memory location. Like as we can see here, at 7842200, kernel 32.dll is loaded up, and that's in the relocation, that's in relock. So if I double left click on that, we get the hex dump of that. If I double click on a data section like the text section, this is the text, I'll get the code. This is the code for kernel32.dll, kernel underscore 32.dll. Like this is the assembly code for DLL, for that particular DLL. Keep that in mind. So if I go ahead and select everything and copy this as, let's say, to clipboard and run this with ASM or any other tool, it'll go ahead and execute kernel32.dll. Yeah, this one. Now this one would be, this is actually dumping a memory location from this to this, and let's see if it has got any values that we can have a look at. No, it does not have any values that are of importance here. This is the data block, and the data block would be going ahead and showing us what happened the last time, if it errored out, and the flag that was set. So we see that it was a success the last time it was run. Now the P header is the portable executable header, like Apache Bench and stuff like that. Like if I double left click on that, it will give me the DOS exe signature. That's of no interest here, to be very honest. It's just like the Apache Bench software launcher, stuff like that, like the signature, like sign. Any application that we create is signed. If it's not signed, it will not execute, or it will not execute properly. So it's signed, and this is like the signature that we are getting here, and it's like the DOS signature. I've shown you what code is, I've shown you what P header is. Now let's move on to the next section. The next section would be the executable modules. Now these are the ones that are being loaded up. These are the executable modules that would be responsible for running this particular application on Windows. So we have got stage.exe. That's my main program. The helper programs would be kernel 32, ntdll, ihl PAPI WS2 underscore 32, ADV API 32, MSVCRT, and debugsoc 32. These are the helper ones, and this is the main program that's being loaded up. So if I go ahead and double left click on that, it will go ahead and take me to the CPU thread and corresponding hexdump thread, and it'll go show me the values that it represents. Now if I go ahead and let's look at CEH chain, it will go ahead and give me the chain that would go ahead and run first. So if I go double left click on this, I would go to, yeah, there you go. This is like from where the execution starts. Like it would go ahead, this is actually the execution of the instructions. Let me scroll up a bit. There you go. So if you go ahead and run these instructions once again using ASM in a series, it will go ahead and produce the same value, and once again you can go ahead and sorry about that, it'll go ahead and inject your own codes here. Like let's say instead of move x, I want to go ahead and add this particular value. So if I do this and do assemble, it will go ahead and let me do assemble once again and show you that this address location has incremented by 1. So if I do this, as you can see here, I'm not sure if you can see this. There you go, the data section. The data section is showing me 004102B2. This is showing me, let me see, yeah, B2, and this is also going ahead and showing the same thing because we have added the same instruction, but this would be different. Here you see that it's loaded up on a different memory location. This is on 130. So this is like the value of the EIP, the instruction pointer, and this would be the value in the instruction pointer that would be that would be passed to the ESP for execution, and once that's passed, it will increment EIP by 1, and it will go ahead and execute the instruction on the address in that particular EIP. So the EIP register is one register. Its value keeps on changing with each iteration of execution of the instruction, of the assembly instruction that takes place. So if I look at the registers here, like in this particular section, let me just drag this a bit to get a better view. Right, so as you can see here, having a bit of a problem dragging here for some reason. Yeah, right. So the EAX register starts from 0, then ECX is loaded up in this particular section. As you can see, this particular memory location. The hexadecimal, the signed, the unsigned, and the CAD locations are given here. These are all the CPU flags, alright, CPU registers, which would be or rather which are preloaded in this stage. For example, the EIP starts from this particular location, so the execution would start from this location. So if I double left click on this, it will take me to the very top. As you can see, I'll show you once again. If I double left click on this, it takes me to the top here, and the first call is of kernel32.dll in this particular scenario, and it would go ahead and call a DEC, decrement on EBX register, and it will go ahead and you know call kernel32.dll and from this particular memory location. This memory location is in the data section. This is in the data section, but you can go ahead and change that as well. Like this is, you can change it to any other location and load any other instead of kernel32.dll. If you're aware of any other arbitrary dll files or any other arbitrary modules that are located in the data section, and if you know the memory location, you can load up that memory location and it'll go ahead and take that particular location and load that value of. For example, if I do a 000000000 and do an add, you see like kernel32 is gone, kernel32 is no more. It'll go ahead and show me the 0000000, but it will not go ahead and give me the kernel32 because kernel32.dll is not present in that particular location, right? So moving on, let's have a look at this section. This is like the jump section. It will go ahead and give me like for this example, as you can see here, a jump is being executed and it's shown by this particular flow chart, like the flow arrow. Like the control is being returned to this location after the execution of these instructions. So once all these instructions are executed, it will go ahead and return to kernel32 dot this particular address from kernel32 from this address. As you can see, it was 78463 DIE from kernel32 dot this particular address, that's 78465E80. So if I double left click on that, and if I say, let's say relative ESP, it would go ahead and show me the ESP value, the stack pointer value. ESP is like extended stack pointer value that it has. And this is like the stage.exe module entry point. This is where the execution starts in when we are running stage.exe, and after the after the execution of these blocks, it will go ahead and return the control to kernel32.dll on this, from this location to this location, from to, right? So if I go ahead and have a look at this, that's DIE, we should be going ahead and there you go. This is D00 and DC. Let me just go ahead and see something. Let me just check this thing out once, just a moment. It should go ahead, yeah, there we, no, not this one. It would go ahead and point a location here somewhere. It would ideally go ahead and give me the section where it would jump to, but I can't find that at this point of time. It's quite possible not to find it because the list is quite long. But I hope that you get, yeah, there we go. EIP there. It's going ahead and showing me the address here. I just hope that, like, you're getting the idea of this particular flow that I am trying to make you understand. I know that, like, this is a bit complicated and you might think that this is not necessary, but once you start debugging programs and developing your own exploits, you'll see that this would come in real handy when you want to go ahead and do application level, like not web application level, but application level bug bounty hunts, where you want to go ahead and find some sort of flaws, like like we got the blue key flaw. Like the blue key flaw was, immunity was used to go ahead and find the blue key flaw, to inject certain codes and see if that particular program runs in a different way, like if it goes ahead and pops a shell or not, if we go ahead and enter certain payloads. And they did exactly the same thing. They went ahead and entered some payloads in certain sections of the memory, isolating that memory first using the flowchart, and then they went ahead and ran it and saw what happens, and they got a shell, and that's what they showed. Like that's how bluekeep or any other exploit works, like remote code execution or local code execution or simple code execution, like code execution as in code injection. So I hope that this particular tutorial was helpful. I know that this is a bit complicated, but if you start using this debugger, you'll find that it's highly interesting and it will give you a lot of clarity. But you'll have to have some understanding of the architecture of the processor and the architecture of the registers of the processor that it uses, like 32-bit and 64-bit varies, like the architecture varies register wise as well. So you'll have to have a basic understanding of that. So you might want to go ahead and look up Intel's manual, like Intel microprocessors manual, because most of the industry level systems use Intel. uh, Not many of them use AMD, but AMD is also used, because AMD is an RISC processor and Intel is a CISC processor. CIS is like complete instruction set computing, and RISC is like reduced instruction set computing. Uh, but that's for another day. Well, I do hope that this particular tutorial was helpful, and thank you for watching and taking the time to watch. And do subscribe to my channel and hit the bell notification icon to stay updated. Once again, this was James from HACK-ATHON, and do have a good day, evening, or night wherever you are. God bless now. Take care. Bye bye.